Hi, in this lecture we are going to discuss again about tests and why they are important. The goals of this lecture is to discuss why tests are important, what are their advantages, and what are the many techniques, or some of the many techniques, that are there available to write good tests. Now, before going into the detail of how to write good tests, it's good to review why testing is beneficial. So the first thing is that we need to understand that tests are like life insurance. So every time that we are going to change something in a system, the test will allow us to detect if we introduce a problem or not. So that in that way, they allow us to have trust in the system and trust in our changes. We can go and modify things more freely without having fear that we did or not break something. So we are not afraid of changing. Also, they will help us in understanding code. That's something that we're going to discuss later in some of the slides. And of course, they will not avoid breaking the system. We can still go inside the system, change stuff, and break it. But tests can help us detect early if a problem was introduced or not, instead of detecting it very, very late during the development process. So remember that the unit test that is not automated doesn't exist. What does it mean? That if I have to manually go and write the test, and if I have to go manually and check the results, they are taking so much time that actually what will happen is that nobody will ever run them or verify them. So automation is something that will help us to do it more and more often. So this is important also because once we wrote the test, we can forget about it and run it again. So we can have hundreds or thousands of tests that will run maybe every night or maybe every couple of hours. Like that, we don't need to remember everything that we did in the past. We have already a set of tests that we wrote in the past and we can reuse them. It's important that you remember that usually we are able to keep 7 plus minus 2 ideas in our head at the same time. So having writing a test, reusing it later is something that is actually a way to flush information. So, of course, the other thing that is important is that programming is about modeling the world, and the world is changing. So we need a way to cope with changes and to trust the way we are doing the changes. So tests will give us some way to structure our way to change the system. So tests will, as I said before, help you to not fear changes. This has many flavors. In one side, if you have a system and you change it, of course, tests will detect if you introduce a problem in the system. In that sense, you can go and try different implementations for already existing code. And if you have tests for that part of the system, tests can already tell you if the new implementation satisfies the existing specification that is in tests. Another thing is that you can write new tests about the already existing system to test that your understanding of the system is correct. So you can actually extend your specification of the test to see if it actually describes the implementation. What is a good thing about tests? So on one side, they will help you find bugs when they appear. So a test that turns red or turns yellow, so a failing test or a test with an error, it is telling you that there's something wrong about the specification of the system. On the other side, if you have lots of tests, you can, yourself as a developer or as a team, you can trust your code base and also transmit that trust to your customers and clients. Tests will also help you to reproduce complex scenarios. So you can, once you have a complex bug, you can write it in a test, even if it is a complex test, and reproducing the test will help you to understand the bug and find a solution to fix it. Also, once you find a bug, you can also write a test for it. So, and then that already existing test will make sure that if in the future you find a regression and that bug appears again in the code base, you will be able to detect it. Finally, a test helps in isolating a problem. Instead of running a test on a really big complex application, you can create small scenarios that reproduce the test with the minimal dependencies. in reducing the dependencies is something that actually will help you to not only find the bug, the actual cause of the problem, but also to fix it much faster. When you're writing a test suite, one of the things that you must ensure is that you are checking, for example, extreme cases, that you're checking for null, zero, empty collections. So, for example, you need to check that a collection has the maximal elements, the no elements at all, and so on. You should also check complex cases or error cases, like exceptions, network issues. These things actually happen in reality, so the system should not only test them, but it should acknowledge that they will happen and be prepared for it. One thing that I think is pretty useful is to write one test for each bug, at least. So every time that you find a bug, you can write at least one test for it to be able to know that in the future you are going to be able to detect that bug if it happens again. Of course, a good test suite has in general a good coverage. So if you have a system and you know that your test covers 80% of your code, you have some trust that there will be less bugs in this part than in this part of the system. Of course, a good test suite will check for abstractions and not for implementations. Implementations will change in the future, but abstractions and specifications are there to stay. Also, one of the things that make a good test suite is that you are going to write many unit tests that test different parts of the system independently. Like that, if one test is failing, it is telling you that some part of the system is breaking and not the other parts of the system. Let's check how all of those good properties of test translate into an example. Here there is a test that checks how color objects are translated into strings, hexadecimal strings, using the convert method. So here we can see that a white color is converted to the FF. The red color is translated to FF followed by zeros, and the color black is translated to all zeros. So what we can see from here and what we can understand from the code without actually looking at the implementation is that the convert method, it will take any color and it will translate it to an hexadecimal representation where the first two digits are the red, the second two digits are the green component, and the third digits are the blue component. So actually, without looking at the implementation, this test is telling us that color green should return 0 for red, FF for green, and 0 for blue. And we could actually know this by just looking at this specification and without looking at the implementation. In the same venue, we can actually look at this other test that is checking that converting from an RR0000 string will actually yield us the correct color. So what this test is doing is that it is taking all the digits from 0 to F to take all the potential possibilities here. And for each of these, it is creating a string that it will have this form. So it will be this plus parameter 0000. Yeah. So, and then it's taking this string and it's creating a color from the string. We expect, of course, that creating a color from this string, so we get a color, and converting it back to the string representation, it should give the same string. So this should be equals to the original string. What this is checking is that from string and the convert method are symmetric in some way. So everything that is given as input to the from string method should be also the output of the convert method. Now, if we take a look also at some tests that check the bit shift implementation in Pharo, we can again look at this test and understand how this bit shift implementation works without actually looking at the implementation details. Two key parts make this test readable. First is that they are actually based on how this works and how it is implemented, of course, because we are just executing it and comparing the result. But also, the writer of this test made really sure to write these examples in binary. Like that, since bit shift is a binary operation, we can actually, just by reading it, understand what this is doing. So if we take a number, so here is 1, 1 in binary, so the 2R is here to indicate the base. So for example, in Pharo, you can do 2R, 1, 1, it's 1, 1 in binary, and you can say 16R to put hexadecimal numbers. So here, if we take 1, 1 and we shift it 2 to the left, this will actually put 2 zeros and put the ones to the left. Yeah. So the result should be 1, 1, 0, 0. Likewise, if we bit shift instead of to the left, to the right using a negative shift, that will cut these two numbers and remove them from the number. So here, for example, shifting 1, 0, 1, 1 to the right by 2, it will discard the 1, 1 that are to the right, and it will keep only the 1, 0. Again, here we can check the same thing as before, as it happened with numbers. We can check that bit shifting to the left and to the right, they are symmetric. And we can understand that property by just reading the test and without looking at implementation. So what does this test do? It takes 100 numbers, and it will just take the number 1 and shift it n to the left and then n to the right. And at the end, we should have the same number. So if I take 1 and I shift it n to the left, and then I shift it n negated, so this returns the negative number for I, that should return 1. Now, of course, I told you before that we can understand the implementation and how it works without looking at the code. Of course, sometimes reading the code is complicated. Some implementations can be tricky and even can be really difficult to read because of even performance reasons. In this case, for example, the convert method that we were looking before, it is defined like this. So it takes first a string, it makes a copy of it. So like that, we have a new string every time that the convert method is executed. And then it is replacing by hand each of the characters, so the second, third, fourth, fifth, sixth, and seventh. So each of these after the numeral character. And it is replacing each of them by a character computed automatically by doing bit operations. So of course, if we had to read this code, it wouldn't be actually clear what this code is doing. It is much more easily actually to understand this code by just reading the tests. So one of the important points to understand the test and to manage the test is that we need to limit the dependency to other components. So imagine, for example, that we want to write a test that transforms some piece of code, so some code here, and we want to transform that code into some other code. Yeah. So our test is actually managing this translation. Now, if this input can only be obtained by calling a compiler on something, that means that our test is going to be dependent on this compiler. So, which means that actually our test can break if our conversion breaks, but also if the compiler breaks. So that means that we have 2 points of failure for our tests. One possible solution to cope with this problem is to make our test independent from the compiler. So removing all this part from the test at all. So what we can do is to extract this piece before the writing of the test, so the input, and reuse that input already generated once and reuse it many, many times in our test. So like that, our test, it can only perform the conversion. When you write tests, think about testing not only the positive, but also the negative properties of the behavior you are testing. So, for example, when I'm talking about positive testing, I mean, if you do the normal stuff, it passes, everything is okay. So we are, for example, if we have a collection, we add an element, now we have that element in the collection. Or, in a more complex case, that you can, for example, log in an application if you use the correct credentials. Now, if you think about also the negative properties of a test, you should test that if you do not behave correctly, the test breaks as expected. So, for example, you should not be able to log in with the incorrect credentials. And not only that, it should raise, for example, an exception with a given code, and also, like that in the UI, you can catch it and show a proper message to a user. If it just breaks and then it closes your browser, for example, then that is not an expected error. Some other positive properties of tests. Tests, as we saw before, they give simple and reproducible examples. Just by looking at the examples in the test, you understand how the code works. Many tests have this property. They also give you executable snippets and examples of code that you can reuse in many other applications. Every time that, for example, you want to use a library that is, for example, an open source library that is online, you can take a look at the test to understand how that library can be used. So then, in that sense, tests do not only give you executable snippets, but they also illustrate the API, so how is the way to use that library. Also, tests will be the most up-to-date documentation because they are actually connected with the code and they are going to be executed. If the tests are broken, you are going to notice. If the documentation is outdated and it's broken, it's more difficult to know. Tests will also check the conformity of new code. If you introduce new code and new variations in the code, or you modify the existing code, tests will actually detect if you broke something. So think about tests as a first client to the code. So you have some code, and instead of thinking about the actual people that is going to use it, think about how you would use it with your test. So your test can be a good first client for your code. And they also allow you to force a customizable design. So they will force you to maintain a clean design that can be executed in a repeated way, that will not dirty an environment with files that are created automatically and so on. So the test will actually force you to add a lot of properties that are inherent to the test in your code. Of course, a good test suite should be deterministic. That means that every time that you run the test, they should give you the same results. That is in contrast with what we call flaky test. Flaky test is something that we are not going to cover in this MOOC, but flaky tests are those tests that actually will randomly have different results. So for example, they will sometimes fail because of random conditions. For example, the network had problems and then they will fail. Having flaky tests or non-deterministic tests actually will minimize the trust that you have in your test, because if you have tests that are failing from time to time, suddenly you will start not trusting your test suite anymore. So keeping a deterministic test suite is important to keep trust. Also, tests are self-explained because when you want to evolve your source code, you want to evolve not only your application, but also the tests, because the tests are the specification of your source code. So the more easily and more self-explained your tests are, the easier they are to evolve. Also, it is important to keep them simple or short, or unit as possible, with as few assertions as possible, because they are easier to maintain. Take into account that tests will change less frequently than the code, because tests will ideally test the API, test the specification, and not the implementation. Like that, you can change the implementation of your source code and keep the same test implementation. And try to limit the dependency to other elements. This is also key to avoid ripple effects in the changes. In conclusion, you should know by now that tests are important, in particular in dynamically typed languages, where actually we get the most guarantees from them. And also, not only in dynamically typed languages, but in any kind of project, actually, tests will help you to deliver complex projects.